In 2024, language models write code, pass bar exams, and hold conversations that feel genuinely human. But this capability did not appear overnight. It emerged from 3 decades of research, each breakthrough building on the failures of the last. This is the story of how machines learned to process language. At its core, a language model does one thing. It predicts what word comes next. Given the phrase, "the cat sat on the," a good model assigns high probability to mat and low probability to dog. Every advance in this field, from RNNs to GPT, is fundamentally about getting better at this prediction task. Before any model can process language, words must be converted to numbers. Word embeddings map each word to a vector, a list of numbers encoding its meaning. In this space, semantically similar words cluster together. The famous example, the vector from king to queen, mirrors the vector from man to woman. Language is inherently sequential. The meaning of a word depends on what came before it. Bank means something different after river than after investment. Any model that processes language must handle word order, long-range dependencies, ambiguity, and limited memory. Early approaches struggled with all four. A neural network is a stack of mathematical layers. Each layer receives numbers, multiplies them by learned weights, applies a nonlinear function, and passes the result forward. Training means feeding in examples, measuring the error at the output, and sending a correction signal backward through the network. This process, backpropagation, adjusts every weight to reduce the error. In 1986, recurrent neural networks introduced a simple but powerful idea: memory. Instead of processing each word independently, an RNN passes a hidden state from one time step to the next. This hidden state acts as a compressed summary of everything the network has seen so far. For the first time, a neural network could handle variable length sequences. When unrolled across time, the recurrence becomes clear. At each step, the cell combines the new input word with the previous hidden state to produce an updated state. Information from early words must survive through every intermediate step to reach the end. This is where RNNs begin to struggle. During training, the correction signal must travel backward through every time step. At each step, it gets multiplied by a weight, and if that weight is less than 1, the signal shrinks exponentially. After roughly 10 steps, the gradient drops below 0.01%. The network cannot learn dependencies longer than a short window. RNNs hit 2 fundamental walls. The vanishing gradient problem means they cannot connect a pronoun to its antecedent 20 words back. The sequential bottleneck means each word must wait for the previous one to finish processing, making training painfully slow on modern parallel hardware like GPUs. Both problems demanded a new architecture. In 1997, Hook-Reiter and Schmidt-Huber proposed the long short-term memory cell. The key innovation is the cell state, a highway that runs across time steps with minimal interference. 3 learnable gates control what information to forget, what new information to store, and what to expose as output. This design lets gradients flow further without vanishing. LSTMs powered a wave of practical breakthroughs. Google deployed them for machine translation in 2016. Apple and Amazon used them for voice assistants. Researchers generated surprisingly coherent text, character by character. Yet the sequential bottleneck remained. Training on large datasets took weeks. and the effective context window rarely exceeded a few hundred tokens. In June 2017, a team at Google published a paper with a bold title, "Attention is all you need." It proposed replacing recurrence entirely with a mechanism called self-attention. The paper introduced the transformer architecture, and it changed everything. Self-attention lets every word look directly at every other word in the sequence, regardless of distance. For each word, the model computes a relevance score against all other words and uses those scores to create a weighted summary. The word "it" can directly attend to its antecedent 50 words back with the same ease as the word right next to it. Distance no longer degrades the signal. Self-attention uses 3 learned projections for each word. The query represents what information the word is seeking. The key represents what information the word advertises. The dot product of query and key produces a relevance score. After normalizing these scores with softmax, they weight the value vectors to produce the final output. Think of it as a soft database lookup, where every word queries every other word simultaneously. The transformer does not run just one attention computation. It runs multiple in parallel, called heads. Each head can specialize in a different type of linguistic relationship. One head might track syntactic structure, another co-reference, another semantic similarity. Crucially, all heads in all positions compute simultaneously, unlocking massive GPU parallelism. Training time dropped from weeks to days. A transformer block stacks self-attention with the feed-forward network, connected by residual links and layer normalization. The input tokens, augmented with positional encodings to preserve word order, pass through the attention layer, then through a 2-layer feed-forward network. In practice, these blocks are stacked many times. GPT-3 uses 96 such blocks. Each layer refines the representation, building increasingly abstract understanding of the text. OpenAI's GPT series follows a 3-part recipe: stack decoder-only transformer blocks, pre-train on massive text corpora, then fine-tune for specific tasks. GPT-1, released in 2018, had 117 million parameters. GPT-2 scaled to 1.5 billion. GPT-3 reached 175 billion and demonstrated that scaling the model and the data together produced surprisingly general capabilities. In 2020, researchers at OpenAI discovered that language model performance follows predictable improvement curves, known as power laws. Double the parameters, and the loss decreases by a consistent amount. Double the data, same effect. This finding transformed the fields from artisanal architecture design to industrial-scale engineering. If you could predict the payoff of scaling, you could justify the investment. At sufficient scale, language models developed capabilities that were never explicitly trained. GPT-3 could learn new tasks from just a few examples provided in the prompt. Later models exhibited chain-of-thought reasoning, code generation, and the ability to follow complex instructions. These emergent abilities appeared abruptly at certain skill thresholds, suggesting that bigger models are not just better, they are qualitatively different. From simple recurrent loops to trillion-parameter transformers, each generation solved the previous generation's hardest problem. RNNs gave networks memory. LSTMs extended that memory. Transformers removed the sequential bottleneck and unlocked attention at any distance. GPT showed that scale itself is a strategy. The frontier now is efficiency, multimodal integration, and deeper reasoning. The next chapters in a story that is far from over.